The sun, it looks like this nice, steady, bright ball in the sky, but there's all kinds of activity happening.
Our sun's just injecting stuff at us, and we need to figure out how it's happening. SunRISE is a mission that's going to help us understand solar temper tantrums. The Sun Radio Interferometer Space Experiment, or SunRISE, is an array of 6 toaster-sized small sats that will work together to study solar activity. Currently, the scientific community doesn't have a strong understanding of these coronal mass ejection.
A coronal mass ejection is a violent eruption of material from the sun's atmosphere, or corona, into interplanetary space. We don't completely understand what causes a coronal mass ejection, but within tens of minutes, those particles can reach Earth and several things can happen. If they pass through an astronaut, they can cause radiation sickness. And when they hit spacecraft, they can actually disable electronics. Your radio stations, your GPS navigation, your ability to text message your friends or send out an emergency signal if you're lost while you're hiking. All of this is dependent on thousands of satellites that are all at risk from these radiation storms. But, and we've noticed something, you never have a major radiation event in space without the coronal mass ejection first giving off a really bright burst of radio waves before the radiation storm starts. What we're going to do for the first time with SunRISE is we're going to image that radio burst. We're going to say, what part of the coronal mass ejection is making these radio waves?
We have these 4 hypotheses about how these particles are accelerated from our sun.
If we look where the radio emission originates relative to this mass of material moving out into the solar system, will tell us something about what's the actual process, what's the physics, the underlying physics.
The challenge we face with SunRISE is we want to image radio waves from frequencies of around 100 kilohertz to 20 megahertz. And in order to form a good image at those frequencies, we'd need a telescope that's something like 10 kilometers across. And we could get above Earth and into orbit to be able to see these radio waves clearly. Unfortunately, we don't know how to build 10-kilometer long structures in space yet.
So instead, this is where we got really innovative in the mission design. And they decided, okay, if we send 6 toaster-sized spacecraft up there and spread them out, we can get the exact same science for lower cost, lower mass, and we can get it now. We have the technology now to do this, collecting all the radio frequencies and doing the science.
We will combine that data on the ground and form basically a virtual dish.
And that's really where SunRISE shines, is because we're able to come back and say concretely, it's this hypothesis. This is how the particles are accelerating. Now can we understand how to predict these things?
It's amazing to think about. Spacecraft about this big, 6 of them, flying around the Earth can give us these fundamental insights. By taking these 6 small things, we end up with actually addressing very big science questions.
This is going to help astronauts out in space. This is going to help us here on Earth. And it's going to just help us better understand this essential ball of life that we have at the center of our solar system.